Hello, everybody, and welcome back to Unit 5, Physical Behavior of Matter, where we will specifically be focusing on the gases. Today, we'll be talking about the gas laws, because we'll be able to differentiate between different types of gas laws that we will be discussing in this chapter. So, the first type of law that we need to talk about in this chapter is the Boyle's law. As you see in this picture, we have a gas in a container. When we look at the first container, we don't have a lot of pressure on this gas, which is why this gas is occupying a lot of space. It has a lot of volume. In the second container now, we are increasing the pressure on this gas. We are bringing those molecules closer and closer together. So they are now occupying less space, which means their volume is decreasing. So Boyle's law gives us the relationship between the pressure and the volume, which turns out to be an inverse relationship or an indirect relationship. Because remember, as we see in this picture, the more pressure we apply on the gas, the smaller the volume gets. So an inverse or indirect relationship is basically just that when you increase one thing, the other thing decreases. When you decrease one thing, the other thing increases. That's what we mean by an indirect or inverse relationship. So that's the type of relationship that we have between pressure and volume of a gas. So let's say if we increase the pressure of a gas 3 times, its volume is going to decrease 3 times. So it's going to be 1/3 of what it was originally. Okay, let's say if we increase the pressure 2 times, like if we double the pressure, the volume is going to decrease by 2 times, which means it's going to be 1/2 of what it was originally. So if we make a graph of the pressure and the volume of a gas, this is the type of graph that we get. This line that we see here is called a hyperbola, and this indicates an inverse relationship. Why is it indicating an inverse relationship? Because look at the first point that we see here. The pressure is 100 kilopascal, and the volume at that point is 0.5 liters. But what happens when you increase your pressure to 150 kilopascal? The volume is now going to decrease to somewhere around 0.32 liters. You keep doing that, you keep increasing your pressure to 200 kilopascal. Your volume is now down to 0.25 liters, and so on. So as you keep increasing the pressure, the volume continues to decrease. So this is the formula that we use for Boyle's law. It's P1V1 equals P2V2. What this indicates is that the pressure and the volume of a gas are inversely or indirectly related. So the P1 and V1 indicates the old pressure and the old volume, and then the P2 and V2 represents the new pressure and the new volume. So these are basically just, let's say, 2 different points on that graph of pressure and volume for a gas. And remember, in Boyle's law, we keep the temperature constant. Okay? So there's a very specific way that we can use to memorize or remember this formula. Let's say you happen to kind of forget how the formula was arranged or anything like that. You can, there's a way that you can use to make your way through kind of figuring out what the formula was. All you have to remember though is that in Boyle's law, we talk about the pressure and we talk about the volume. But let's say you forgot about the relationship, that they're inversely or indirectly related. Just remember that Boyle's law has pressure and volume. So we start with the ideal gas law equation, which is PV equals nRT. From this equation, we only need the pressure and the volume because Boyle's law only has the pressure and the volume. So the things that we need, we want to make sure that we can bring them to one side of the equation in the ideal gas law. In this case, we are lucky because both pressure and volume are on the same side of the equation. So what we can do is we can basically just take that pressure and volume part and we can double them. So we can say we can put P1V1 on one side and then we can put P2V2 on the other side, and that is going to give us the Boyle's law. Okay, so that's kind of like an easier way to remember these equations. The next type of law that we need to talk about is Charles' law. When we look at this picture here, what we see is that we have a bunch of inflated balloons or filled balloons, and we are putting them in liquid nitrogen. Now, liquid nitrogen is very, very cold. It has a very low temperature. So what you notice here is that when you put your balloons, inflated balloons, in the liquid nitrogen, which is at a very low temperature, the balloons are going to shrink, which means their volume is going to decrease. Remember, volume is the amount of space that something is occupying. So when the balloons are filled, they're inflated, they're occupying a lot of space, they have more volume. When the balloons are shrinked, they're now occupying less space, their volume is lower. So what we notice then as we take the balloons out of the liquid nitrogen is that now they're at the room temperature. Their temperature is going to increase eventually, and then as the temperature is increasing, their volume is also increasing. They are becoming inflated again. So Charles' law gives us that relationship between temperature and volume. So what, as we notice in this example, when the temperature is lower, the volume is also lower. As we increase the temperature, the volume also starts to increase. So that represents a direct relationship, and that's what Charles' law gives us. That the volume of any gas is directly related to its temperature, which means if the temperature is higher, the volume is higher. If the temperature is lower, the volume is lower. So just remember that the temperature of gases has to be in kelvins. Do not ever forget that. Make sure that the unit of temperature that you're using is Kelvin. So let's say we increase the volume of any gas by 3, the temperature is also going to increase by 3. So when we make this graph between volume and temperature, this is going to be a straight line like this. And that straight line represents a direct relationship, because if we are increasing one thing, other thing is also increasing, decreasing one thing, other thing is also decreasing. So here's the equation for, or the formula for Charles' law. V1 over T1 equals V2 over T2. So once again, the V1, T1 represents the old volume and the old temperature. V2, T2 represents the new volume or the new temperature. And these are basically, if I have to put that in simpler words, these are basically just two different points on the graph. Or in other words, let's say we are doing an experiment. We say that this is the volume of the gas that we start with, and this is the volume of the gas that we end up with. And this is the temperature of the gas that we start with, and this is the temperature that we had at the end. So in some cases, you're not given one of those factors. Like they'll give you the initial and final volume, they'll give you the initial temperature, and you're supposed to find the final temperature. So this is the equation that you use to do that. So same thing with the Boyle's law that we discussed earlier. That's why we have these formulas. Just one thing to keep in mind is that in Charles' law, the pressure is kept constant. So remember, in Boyle's law, we were keeping the temperature constant. In Charles' law, we are keeping the pressure constant, which means the pressure is not changing. So once again, there's a way to remember Charles' law. Let's say you forget that volume and temperature are directly related to each other. We start with the ideal gas law again, PV equals nRT. And remember, for Charles' law, we only need the volume and the temperature. So what we want to do here is we want to go ahead and bring both of them on the same side. So let's start with the left-hand side, the PV, okay? And on this side, we have the P, which is extra. We don't need the P. So what we'll do is that we'll divide both sides with the P. When we do that, the P cancels out on the left-hand side, but it stays on the right-hand side. So this is what we have. V is now equal to nRT over P. Okay? Now, we want to bring the T to the other side, because remember, we only need the V and the T on the same side of the equation. Everything else we don't need. So the T is multiplying here, which means we'll have to divide this on both sides as well. So we have V equals nRT. We divide the T on both sides. Now the T on the right hand side cancels out, and this is what we get. V over T equals NR over P. Okay, so now that we are done with this, we have the V and the T, the volume and the temperature on the same side. We can just go ahead and duplicate that or do like the V1 over T1 equals V2 over T2 thing. And that gives us the Charles law. Alrighty. So the next type of law that we have is Gay-Lussac's law. So if you guys look at this temperature, what we notice here is that in the first container, we have a gas which is at a very low temperature. Now, remember, we said that temperature is the average kinetic energy. So when a gas has a lower temperature, its molecules are not really moving very fast. When they are not moving fast, they have very low kinetic energy. And they are also not exerting a lot of pressure on the walls. So low temperature equals low pressure. Okay, in the next container, now we are increasing the temperature. As we increase the temperature, what happens is that the particles start moving faster and faster and faster. And remember, when those particles are moving, they are constantly colliding with the walls of the container. They are colliding with each other. They are exerting a lot of pressure. So basically, when you increase the temperature, the pressure also increases. So Gay-Lussac's law gives us the relationship between temperature and pressure. That's what you have to know. So pressure and temperature of a gas are directly related because remember, low temperature equals low pressure, high temperature equals high pressure. So this is the equation that we have for Gay-Lussac's law. P1 over T1 equals P2 over T2. And once again, the P1 T1 represents the old pressure and the old temperature. P2 T2 represents the new pressure and the new temperature. So let's say you're given a question saying that this is the pressure that we started with, this is the pressure that we ended with, this is the temperature that we started with. What is the final temperature? This is the equation that you use. Okay, just one thing to keep in mind is that your temperature has to be in Kelvin. Do not ever forget that your temperature has to be in. So once again, there's an easier way to remember that. Let's say you don't remember that the pressure and the temperature are directly related. You start with the ideal gas law and remember that we only need the pressure and the temperature in this case. So basically, for the most part, if you're given a calculations problem, they don't even ask you that what type of law is this. So you don't even have to name that this is Gay-Lussac's law. You just look at what's given in the question and that's what you use to figure out what are you looking for. So let's say your question has given you the initial pressure, the final pressure, initial temperature, and you have to find the final temperature. So you will know that we are talking about the pressure and the temperature. You don't even have to know that this is Gay-Lussac's law. That's how easy this is. So let's say your question told you that you only need the pressure and the temperature. So that's what we want to bring on one side in this equation. So we start with the left-hand side, where we have P as extra stuff. That's what we want to get rid of. We want to bring that to the other side. So we go ahead and divide both sides by V. When we do that, we can go ahead and cancel out the V on the left-hand side. And now on the right-hand side, we have P equals nRT over V. Okay? Now the next thing that we can do is we can go ahead and divide both sides by the T because we want to bring the T or the temperature to the left-hand side. So this is how we do that. The temperature cancels out on the right-hand side. And so now we only have P over T equals NR over V. So all that we are concerned with is P and T. So we can just do P1 over T1 equals P2 over T2 thing to duplicate that P over T part. And that gives us the Gay-Lussac's law. And that gives us the equation to solve our question whenever it's given. Okay, so the next type of law that we have is combined gas law. What this law does is it's just P1 V1 over T1 equals P2 V2 over T2. This is basically just a combination of the three laws that we just discussed. Boyle's law, Charles' law, and Gay-Lussac's law. Okay, and the good part about this equation is that you don't have to memorize this because this is given in table T in your reference table packet if you ever might want to go and check it out. So remember, Boyle's law was P1 V1 equals P2 V2. Charles' law was V1 over T1 equals V2 over T2. And then Gay-Lussac's law was P1 over T1 equals P2 over T2. So what this law did was that it just combined all three of those factors from these three different laws, and it made a combined gas law equation. So if you have a question where you don't just have the initial pressure and temperature or initial volume or temperature, anything like that, let's say you have all three of these quantities, actually all six of these quantities or maybe five of these quantities, and you're supposed to find the sixth one, then this is the equation that you use. If you're given three quantities, you're supposed to find the fourth. That's when you use the other three laws. And once again, remember for this one as well, you want to make sure that your temperature is in Kelvin. Don't ever forget that. Okay, so the last type of law that we have for this chapter is Avogadro's law. So let's say here we are looking at two samples of different gases. Both of these gases have the same pressure of 2 atmosphere, and they are at the same temperature, 273 Kelvin. Okay, now what Avogadro's law says is that when we are looking at the equal volumes of two different gases who are at the same temperature and same pressure as these two gases are right now, then they contain the same number of molecules. Okay, so the numbers that this law gives us is if we have two gases. So let's say both of these samples that we have on our slide right now, let's say both of them have a volume of 22.4 liters. Then they are going to have 6.02 times 10 to the power of 23 molecules. That's the number of molecules that they are going to have. And these number of molecules are equal to 1 mole. Okay? Now let's say rather than having 22.4 liters, let's say I decrease that volume by a half. Let's say I say that for both of these gases, I only have 11.2 liters. How many molecules are they going to have now? Well, the molecules are also going to be decreased by one half. So now they are going to have 3.01 times 10 to the power of 23 molecules. And how many moles do we have now? 0.5 moles. Because remember, we decrease the number of molecules, we decrease the volume. So here we see three different gases. We see argon, oxygen, and nitrogen. Both of them are at the same pressure of 1 atmosphere and the same temperature of 273 Kelvin. All of them have the same volume. They have a volume of 22.4 liter. So whenever we have gases that have the same volume of 22.4 liters, they have 6.02 times 10 to the power of 23 molecules, which is equal to 1 mole, which is why all three of these gases have 1 mole, or we have 1 mole of all three of these gases. So when we put this in the equation, we get V1 over N1 equals V2 over N2. So once again, as always, the V1 and N1 represents the old volume and the old amount of gas in moles. And then the V2 and N2 represents the new volume and the new amount of gas in moles. So remember that in this case, in this law, we keep the pressure and the temperature constant. So once again, for this law as well, there's a quick way to remember that what is the relationship between the volume and the number of moles. Remember, it is a direct relationship. If you increase the number of, if you increase the volume of a gas, the number of molecules increase. If you decrease the volume of gas, the number of molecules decrease. So it's a direct relationship. But let's say you happen to forget that, You once again start with the ideal gas law, and you, in the question that you're given, you have only see the volume, like the initial volume and the final volume, and you see the initial number of moles, and you have to find out the final number of moles. So you know that you're looking for the volume and you're looking for the number of moles. So on the left hand side, the pressure is extra stuff. We want to get rid of that. So we'll go ahead and divide the pressure on both sides. It gets canceled out on the left hand side. We only have it left on the right hand side. So V is now equal to nRT over P. Then we want to bring the N, or the number of moles, to the left hand side. Because it is multiplying with the R and T right now, we'll go ahead and divide that on both sides. So this is what we get. V over N equals nRT over Pn. The N cancels out on the right hand side because we have already brought that to the left hand side. And this is what we get. V over N equals RT over P. But remember, we are absolutely not concerned with whatever we have on the right side. We are just looking at the V over N. And we can duplicate that to write V1 over N1 equals V2 over N2. And remember, guys, please don't ever forget that this N is supposed to be a lowercase n. Okay? Alrighty, so this was it for all of the gas laws. And I will see you guys next time.